it works. Cool. So to seminars, and our goal that at the end of the day, all students understand all basic concepts, because all of the stuff we discussed today will be needed in all practical assignments, homeworks, and so on of the course. So please pay attention to this material. For some students who already know all this stuff, I will suggest like a more complicated task, where you will just write some code to see some interesting effects. And I suggest that I can now send the link to this task to the chat. But I suggest that I now talk some basic things on PyTorch. Then while all students will solve the first task, at this moment I can briefly describe the complicated task for like of the students who want to solve it. I didn't speak English for several months, so it may be not so good as you maybe expect. Sorry for that. So we have a repo on GitHub where there are all our tasks. So I now send link to the chat on this repo. So, okay, the first seminar will be on high level of PyTorch interface. So we will talk how to train like the most standard scenario of using PyTorch, of using any deep learning framework, training convolutional neural network on the Venice data set, of course. So I suggest that everybody starts listening to me, and if at some point somebody understands that he or she is very familiar with all the material and everything is obvious, then this student can solve that complicated task. I will send link to which now. All other students go with me on PyTorch, okay? So I now send the link to the complicated task to the chat in here in Zoom. But okay, again, I suggest that you firstly listen to what I will tell now. Do you see my screencast? I try always, thank you. I try always look at the chat. So if you have questions, you can write them there. Or maybe just ask using microphone as you prefer. Okay, so we will train convolutional neural networks. Actually, we'll train Linnet on a Venice dataset at this seminar. And first, so this is like a very standard scenario of using PyTorch. So like we will, so now we will go through some example where I will show you how all it works, and then you will repeat it like in your implementation. I do not send you a link to the task right now, because I suggest that firstly we will go through my example, and then you will have time to write your own code. And to run this code today, you actually don't need some GPU. So training Linnet and Venice dataset is not so computationally expensive, so you can do it even on CPU. This is not true for the complicated tasks. So if you try to solve complicated tasks, try to use something like Google Colab, okay? What else? I think this all now for some organizational questions. So now let's move on to the to our material. So let's briefly go through the standard example of using PyTorch for training some neural network. So we now will look at some standard samples of the code that you should write when you want to train your neural network. Of course, if you have some new data or some new network, you will modify some parts of this code, but the general scenario will be the same. So please pay attention to these things. So we import Torch. Torch Vision is a specific package for working with vision in Torch, and usually it's also used. So this is so here we define device on which we will work. It is either GPU or CPU. What is depending on what is available for in our system. Here we define some hyperparameters. And of course, the first thing we do is loading some data set. In our case, it is a MNIST data set. And in PyTorch, there are basically two, don't know this word, okay. Do things for working with data sets. So firstly, you create like a data set object. We do it here. And then you also create data loader object. So we do it here. So the first object stores all your data, all your training data and testing data and whatever other data. And the data loader, the purpose of data loader is to generate batches for training or for testing. Here we use standard data sets from PyTorch, loaded from Torch Vision. So here we used MNIST. We specify some path where to store our data. Train true and train false defines which partition data set we want to load. And transform is, it may be some sequence of transforms. So this is like basic functions that you can, you want PyTorch to conduct with your data after loading. So here we just say that we want our data set will be Torch tensor, not NumPy tensor. So it will be converted from NumPy to Torch tensors. And on this seminar, we talk about again high level of PyTorch, and on the next seminar, starting at 12:15, Alek will tell you about low level of PyTorch interface. So you will get familiar with all these Torch tensors and other basic operations in Torch. We decide usually we usually we hold seminar on low-level interface first and then on high-level interface, but this year we decided to switch them, and it's also an acceptable scenario. My English is so bad, sorry for that. It's morning, and it's really bad. Можно я буду говорить по-русски, пожалуйста? Нет, нельзя, ну ладно. Или Дмитрий Александрович уже ушел. Okay, so we defined data sets and data loaders. Now let's define our model. So model in PyTorch is usually inherited from an N module. And this allows these things. So you implement basically two functions. So how to initialize your model and how to perform forward pass. And then since you inherit from an N module, some functions are also, some methods are also available for you. So for example, an N module will automatically gather all parameters of your network if you ask to, or some stuff like that. So inheriting from an N module allows using some functions from Torch for your class that you do not define, but they are commonly used, and so you don't waste your time for implementing them. Okay, so here we define some basic convolutional neural network. Init method of the class. In this method, you specify your architecture. And in our course, you will have several assignments where you will need to implement some different neural networks. So you will define usually these classes, and the init function, you specify all layers you will need. So here we need basically two levels. Like layer 1 is convolution plus batch norm plus ReLU plus max pooling, and layer 2 is in a similar way, but this is the second layer. So the difference in these layers is the parameters, of course, so they have different sets of parameters. And finally, we have fully connected layer here in this example. And forward method is needed to define the forward path. So how your tensor goes, input tensor X goes through the network. So here we use layer 1, layer 2, then we reshape to allow using fully connected layers. So here out in this line is a tensor of like batch size and the dimensions of your like image. So it will be batch size, width, height, and number of channels. And for fully connected layer, you need batch size times some fixed dimension. So to convert width by height by number of channels to like some flattened direction, you use this reshape here. For example, you can see here that when we call layer 1, that is first sequence of convolution, batch norm, and so on, we did not write here self.layer1.forward, because here, if you mention, we define forward function. But you can just type the name of your the component of your network and just call it using braces. So, and then module, this thing, it redefines braces, so that you calling this layer with braces results in calling forward path. Okay. So here we define the class for our neural network. Now we need to define an instance of our neural network. We do it here, and we move it. So we define it, and we also move it to some device, to our device. This device was introduced at the beginning of this file here. And in PyTorch, you should move all tenders you have all on one device, is the CPU or one GPU, for example. And usually, what are these objects you need to move? So it's your model, and these are your batches, two things. So batches that are input to the network and the network itself. And this is the moment where we move model to the device. Okay, so now we define some criterion. This is cross entropy in our case, and cross entropy loss in PyTorch incorporates torch. Incorporates softmax. So if you see here, we do not have softmax because softmax is inside our loss. And finally, we define optimizer that we will use for optimizing our parameters of our network. In this case, it's Adam. So here we specify all the parameters of our model and learning rate. Learning rate is our hyperparameter. And model parameters, again, let's see. Our model is class of our convnet, and this is our class of convnet. So we have only forward method here. So there is not actually method parameters that we defined, but this method parameters is inherited from an N module. So this function gathers all the parameters of all your layers. And actually in our network, we have parameters here and here. So we have, and here also. So there are parameters in convolutional layers, on two convolutional layers, and in fully connected, 3 layers with parameters. Batch and batch norm too, of course. In ReLU and max pooling, there are no parameters. Okay, so we defined our optimizer, and now the main thing in training neural networks is training loop. Here we do cycle for epochs. Now epochs is set to 5 in this example. And at each epoch we do a cycle on batches. So here we use our train loader, and for something in train loader will result in yielding our batches. And standard loaders load X and Y as two things. So these are our images, X's, and these are our targets or labels. So images is basically a tensor of size, as I said, batch size, heights, widths, and in the MNIST dataset, it's the last dimension is 1, so we only have one channel in MNIST. If we would load some other dataset, for example, CFAR, it would be 3 channels, red RGB, for example, or other number of channels. But in MNIST, only one channel we have because we have black and white images. And labels is a vector, a tensor of size, batch size. So for each object, we have a class label here. So we move both tensors to device, to our CPU or GPU, so that they will be on the same device as our model. And now some standard steps go. So we perform forward pass by calling our model, like calling with these brackets. Again, these brackets are redefined as calling forward method. Then we compute our loss function. And then to perform backward pass, 3 standard commands. So you zero gradients using this command, then you compute gradient using this command, and then you perform step of your optimizer. So 3 standard commands you will always use to train your neural network. So during the first command, all the gradients are zeroed for all tensors and your network for all parameters. Then here, the network performs backward pass and computes gradients, and here parameters are updated using Adam in our case. And you will tell about some details on backward pass and PyTorch, how it is performed with the leg in the second part of today's seminar. So after at 12:15. And now we perform some printing. Okay, so this was training, and now testing stage. So for testing stage, we firstly move our network, we change the mode of our network. So this eval function switches mode between training and testing. It may be needed for some layers where the behavior of the network on the training and on the testing stages are different. Could you give examples of these layers in the chat? So the layers that for which the behavior of the network in training and testing stages are different. Thank you. Thank you. Okay, so yes, we choose truth. So here we have batch norm for which during training we use statistics over batches, and during testing we use cumulative statistics from the training data set. And yes, dropout is another example where during training we sample binary masks, and during testing we just use deterministic parameters, deterministic forward pass, and multiply each neuron by 1 minus p or like that. Okay. So to perform testing, and during testing we just want to compute accuracy, we do this with torch no grad. This operation means that we do not compute gradients in all this code, and it saves our memory, so we do not need additional memory for storing gradients with this command. And here we again perform cycle over loader, now over test loader. Again, we move our X and Y images and labels to our device, perform forward pass, and get predictions. So predictions here have the same shape as labels. So it's the size of batch size. Oh, No, of course no. It's not the truth. So here outputs have the shape batch size times number of classes. And then we will use this number of classes to make predictions. So this is, yes, of course, this is not this is the same shape of labels. So output is of shape batch size times number of classes. So then we make predictions by choosing arg maximum over each for each object over classes. So arg maximum in PyTorch usually looks like this. In the newest version of PyTorch, there is argmax operation also in a NumPy-like manner, so torch argmax. But previously it was used like that. And we compute the portion of correct predictions here. And this is a command if you want to save your model. So saving model in PyTorch looks like you use torch save command and you use this function model state dict. This function model state dict again gathers all parameters from your network and makes a dictionary of them. So the dictionary has keys like the names of the parameters, for example, fully connected where weight or fully connected where bias, and the weights itself like torch tensors. And this dict will be saved to the file model ckpt. And this is the standard way of saving models in Torch. So you do not save the class, you only save the parameters. And if you want to load your model, you firstly define your model using the same class as in this script. And then you load the parameters and assign the parameters to their values, to their tensors. Okay, so now let's look at our task. What will be your task? What will you do? So here we will also train some convolutional neural network on a Venice data set. The network. So here we will go through all these steps, and the goal of this task will be that you. So your goal is to rearrange the code. So you will have some functions here that you need to fill in. And the code you will write there is very similar to the code in the example 1 that we reviewed now. But you need to understand which functions go where, so to organize your code in some good way. Here we load a MNIST from NumPy. This is to show you an example of. So here we assume that the MNIST is our like custom data set that we have on our disk, and you just create your own data set here to store it. So some imports, you will need a util module. Yeah, I will show you where. So it's in the same repo. So basically, you load 4 NumPy matrices: X-train, Y-train, X-test, and Y-test with the MNIST. So these are all NumPy objects. And if you have this NumPy dataset, how can you obtain PyTorch dataset? Yes, also here we perform splitting the data. So we shuffle all indices, and the indices for train dataset are selected here. And here this is the shape of X-train. So it's this is the number of objects. This is heights and widths, and this is our one. We only have one channel as we discussed. So if now we want to convert our NumPy dataset to Torch dataset and to Torch data loader, and to do it we need 2 functions. The first again creates dataset, and the second creates data loader. And for dataset here we take NumPy dataset of X and Y. And then we create loader using data loader, and For data loader, we of course specify batch size because data loader create batches, generates batches, so we need batch size here. And for our seminar purposes, we here create shortened version of the data set with only 15,000 objects for speed purposes, and we create train and validation loaders here. Okay, so these are our training data. This is our training data. And now your task will be implement Linet architecture here. And no, doesn't work. Okay, this is a reminder on what parameters does convolutional neural network have. So here you, oh, sorry, this was this solution. Let's open it on GitHub without solution. Okay, so this is a class you need to implement. You need to implement init and forward methods. So here you define the components of your network, all the layers you need, and here you define forward path. Then you create network, count the parameters, and also you need to train your neural network. So here we create criterion again, device, and so on. And so you need to define your model and write code there. And also you need to define a train epoch function and evaluate loss and accuracy function, 2 functions that we will use during training. So our training basically looks like this. We conduct cycle over epochs. At each epoch, we call train epoch function. So this function should go through all batches, perform forward, backward path update weights. Then goes to evaluate loss accuracy calls. So for the first call computes loss and accuracy for training data set, for training set, and the second for validation. So you will control both training and validation progress during training of your network. Controlling both quality on both sets, training and testing, is important because in this case you can see whether you have underfitting or overfitting for training your neural network. So for example, if at some moment your training accuracy is about 100%, but your validation accuracy goes down, then you have overfitting. And if you're, for example, you see that your training accuracy is about 50% at the end of the training, it means that your network is underfitted. So do not control only train accuracy, but not only control validation accuracy, but also train accuracy during training. And here are some printings. Okay, let's remember what is Linet architecture, because you will need to implement it now. So Linet consists of 2 convolutional layers, here and here, and then 3 fully connected layers. So the first convolutional layer computes first filters from the input image, and then the same does second convolutional layer. What to pay attention to? That in our code, oh, it's not our code. Where is our code? In our code, our X has shape. Too much code. Each object has shape 28 by 28. So this is the height and width of our network. And in the image we saw, classic image about LINET, here is 32 by 32. So you need to recompute the parameters of your convolutional layers here. And let's do it all together. So where is our example? So in convolutional, for convolutional layer, you need to specify number of input channels, output channels, and kernel size, and some other parameters also, but we will use their default values. So in, out channels, and kernel size. Please write down these numbers for the first layer, for this one. So which parameters we will use for this layer? Input channels, output channels, and kernel size. Okay, so let's do it all.
One, kernel size 5, and output channel 6.
Yes, so let's look. So input channels here are from our training data. And in training data, we have grayscale images, so only one channel. So yes, for first convolutional layer, we have only one input layer. Then one input channel. So the number of output channels is from this image. This is 6, because here we have 6 maps, feature maps. So I will write to the chat: in channels equals to 1, out channels equals to 6 for the first layer. And let's also compute kernel size. So here our input is 32, output is 28, and we do not yeah, there are correct answers in the chat. So our filter does not go out of the borders of the image. So you can see here that our output image is by 4 smaller than the input. And this means that our kernel size is 5 by 5. Yes, so as Alexander correctly wrote in the chat, our kernel size is 5 here. Okay, then goes max pooling. So 6 filters goes to 6 filter, and 28 by 28 here now becomes 14 by 14, because we perform max pooling here. Max pooling layer. So for max pooling layer, we will have kernel size 2, because 28 moves to 14. Okay, then the second convolution goes, and for it we have 6 input channels, 6 input channels, and 16 out channels, because it's shown in our image. And what again is kernel size? So again, we have input 14 by 14. Here we have 10 by 10. It means that if we are in some point, we have 2 pixels to the left, 2 pixels to the right. So again, kernel is 5 in the second convolution. And now most complex task in the is in this okay, in the whole assignment. We need to compute the dimensions for fully connected layer. So convolutional layers have parameters: in channels, out channels, kernel size, and fully connected layer has 2 parameters: input dimension and output dimension. And so output dimensions are written here. It's like 120, 84, and 10. So we'll have 3 layers. These are their output dimensions. But what is the input dimension for the first fully connected layer? To compute it, you need to like take the input shape and compute what will be the shape of this tensor, and then understand how many values are in this tensor. And let's compute all together. I write to the chat, so please open the chat. So our input is, in the image is 32, but in our data, if you remember, we have 28 by 28. So after first convolutional layer, we will have a -5. So here it's 28, in our -4. In our case, it will be 28 minus 4, 24. Then goes first pooling layer. So 24 now becomes 12. Here. Then it goes to one more convolutional layer. So 12 becomes, again, 12 minus 4, it is 8. So after this layer, we will have 8 by 8 images, intermediate images. Then goes max pooling. So 8 by 8 becomes now 4 by 4. So here, instead of 16 by 5 by 5, we will have 16 by 4 by 4. And now to compute the input dimension to our fully connected layer, we just need to multiply these dimensions. So it will be 16, because we have 16 filters of the last convolutional layer. 16 times 4 times 4. And you will compute it in PyTorch, what is the exact number. Okay, so we discussed the parameters of our net architecture. I will also send you a link to this image because it does not upload in our notebook. Also, I send you the link to the task. So you now download this Jupyter notebook, open it on your laptop or computer where you have run all the cells. And also please download util.py model. So you download lab CNN English and util. And also so you can use the examples of the code. This, for example, this example one. And what you need to do, you need to fill this CNN model, train epoch, and evaluate loss accuracy epoch, evaluate loss accuracy functions. Are there students who solve complicated tasks on loss surfaces? If yes, please write to the chat. Okay, so you now download this task and solve it. You will have time, I think, till the end of the seminar, so till 12. And I will, to be able to help you in some way, I will create breakout rooms in Zoom. So you will be like in comments of 3 or 4. It is not command work, you all work individually, but breakout rooms are needed so that I can come to your breakout room. You will only see your 3 like roommates. So I can come to your room and you can share your screen if you have some problems, and I will help you. So your screen will be seen by me and your 3 roommates. And in case we do not have these breakout rooms, we will be only work like in this big chat. And if some student shares the screen, all other students see it, so it's not convenient. So we will use breakout rooms. One more note, you will need at some point I suggest you here to add long here. And this, so here we have float and here we have long. I will send this code to chat in Zoom and also to chat in Telegram. Okay, so please add long here. And I will also send links to the tasks to Zoom or to Telegram. So if you have some general questions or problems, please say it now. In about 5 minutes, I will open breakout rooms so I can help you individually. And also I will maybe close these rooms at some points so that we can discuss the solution all together or some parts of the solution. And I will send you like correct code in the chat at some points. And again, at this seminar, we look at high-level interface of PyTorch, and on the next seminar, you will look inside low-level interface of PyTorch. So how to use PyTorch in NumPy-like manner, so you can implement all any architecture or algorithms. And if you need to implement some complex architecture, and you will need in our course, you will change your code. So you will write your code in your model. So this class that we inherit from an N model, and where we define forward pass. So in this class, you will need all these low-level functions. Of course, not only here, but this is the main part where you will need them. So if you have like standard architecture, for example, in it, you can just use layers from Torch, convolutional layers, fully connected layers, and other layers. But sometimes you will need to implement your own layers. In this case, you will need low-level interface. Okay, so now I will open breakout rooms. If you have some questions, there is a button, raise your hand there, or ask for help. I don't remember exact name, ask for help. So if you press it, I will see the message that you ask for help, and I should come to your breakout room. So I open rooms. You now have message that you can join your room. Feel free to chat there. So let's see my implementation of CNN. Who doesn't want, please don't see. You can continue working on your task. Let's discuss the solution for the first task of creating CNN model. So we need two convolutional layers. I call them conv1 and conv2. So this is conv2 there. So you just use them, for example, from the from the example file. You can use the same way. So we discussed for first convolution input channels 1, output channel 6, kernel size 5. For the second convolution, input 6, same as here, of course, output 16, kernel size again 5. I do not define max pools here because I will use them from torch and functional model. I will say what it is now, but you can do as an example and define max pool here in this way. So because our max pooling has kernel size 2, we write it here. So in Torch, there are two main models for basic NN methods. So this is model Torch NN that is usually imported as NN. Torch NN, where it is, Torch NN. So all layers or all standard layers and some architectures also are implemented there. And also there is Torch NN functional model that is usually imported like Torch NN functional as F. So all operations that are functions are implemented here, for example, sigmoid, softmax, pooling, and so on. So these are operations that do not have parameters. So if a layer has some parameters, it is implemented in NN. And in NF, in functional model, there are only layers that do not have any parameters. And so they can be not like classes, Python classes, but Python functions. So they are like functional, called functional and stored in functional model. And here I will use this F, but you can also import it from NN, it's equivalent. So fully connected layers. First fully connected layer is output dimensions. We take them from an image, and input dimension is as we computed 16 by 4 by 4. And the same, all the same thing here. So I wrote in the chat that you should not forget ReLU activation after all linear layers. So we add non-linearity after linear layers, and linear layers are both fully connected and convolutional layers. So after convolution, we also insert ReLU. So we take our X input, pass it to first convolution and to ReLU and obtain X1. Then goes max pooling. In a functional model, it's called like that. So we pass X here and kernel size 2. If you use this line, so you define max pooling in init. So here instead of F max pool 2D, you write self max pool instead of this, and do not write 2 here because you already specified it here. Let's comment on it. Then goes the second convolutional layer again with ReLU and the second max pooling. So convolutional ReLU pooling, and now we need to reshape what we have. So again, example, you can take this code from an example. So we use reshape function, and this x4 shape 0 returns batch size, and we can write -1 here to obtain vector. And again, do not forget about ReLU. So first convolution, second convolution, and we do not insert ReLU after the third fully connected layer because here goes softmax, and softmax is incorporated as cross entropy loss, if you remember. So I will send this code to our chat in Zoom, not in Telegram. I don't want to send it to Telegram because there are other students from other course from MFTE there. So I don't want to share solution with them right now. So I only send it to our Zoom chat here. for those students who want to use it. And we have here 44,000 parameters. It looks like actually we do not need breakout rooms because there are no many questions. If there are some questions, you can write to me in Telegram in personal messages. And yes, in our course we will have like this. So you have lectures, of course. You will also have some theoretical seminars where you will solve some problems, theoretical problems, and also there are practical seminars like what we have now. So where we give you some task and you solve it, and then so on. So these practical assignments for the seminars, you don't need to upload your solution everywhere, so it's only for your own usage. We do not check your solutions for these tasks at seminars, at practical seminars. But all the things we discuss here, as I mentioned at the beginning of the seminar, are very important. Because you will need all this basic stuff about interface of PyTorch and how PyTorch works. So it's very important that you not only can copy code from Stack Overflow. It's very important that you understand what each line of the code does, and so you can write code by yourself. So this is the purpose of this task. Why we solve it now? Daria asks question in the chat. Daria, I suggest that I open breakout rooms and I will come to you now and we'll solve your problem. So let me show my full solution. So in training, epoch function, we do cycle over training loader. Here, this long is needed to make all y elements of long type. If you inserted long in the loader, as I suggested you before, so you don't need this long here. Then we do zero grad, do forward pass, compute criterion, compute backward, and optimizer step. So all the standard operations. Making zero grad before or after forward pass, I think it doesn't matter.
Sorry, but why do we need Y to be long?
This is the requirement of PyTorch. So it okay, maybe they fixed it in. I don't think they fixed it in the new version. Okay, so if you remember, when we compute cross-entropy loss, we select elements as based on indices, and these indices are classes. So even in NumPy, if you want to select some indices, if these indices are float type, it will raise an error, if I'm not mistaken. But in Torch, it will raise an error. So your indices should be int or long, but not float. And here we do it.
Okay.
And the moving model to train mode is needed to achieve that we switch the regime for layers that needed. And in Torchival, we use Torch no grad because we don't need gradients. Again, do pass through loader. It will be either testing or training loader, move it to device, compute forward pass, compute criterion, and then compute accuracy and loss in the same way as in the example. So if you need my code, if you want me to send it to chat, please write to the chat. I will do it. But now let's look at the results. I think it's most interesting part. So here our loss goes down, training loss. Testing loss at some point becomes increasing. It's okay. So testing loss increases mainly because your first layer without weight decay, if your first layer its norm becomes greater and greater, because if you remember cross entropy or logistic loss function, they have optimum at infinity. So if you make your probabilities a bit higher, correct probabilities, then your loss becomes less. So the norm of this last layer is not limited, and if you do not use weight decay, usually your test loss starts increasing at some point. But accuracy, but everything should be okay with accuracy. And here our accuracy is about 99 on training and about 97 on testing, like that. And also there is a visualization task here. So to perform visualization, you select some first images from training set, move them to the device, and then perform, just use the first convolutional layer, call it to obtain Y. And here we see that standard convolutions. So we learned some kernels that find some gradients on the images in this way. So compute some features of images. And to visualize the second layer, we again do X in the same way as create X in the same way. So from training data, and use Torch from NumPy for that. And you will talk about these functions like Torch from NumPy and so on, and move into the device in the second, after the break. Send the code. Okay, I will do it. And here we repeat the first part of our forward pass. So we use convolutional layer, ReLU, max pooling, and here visualizations from this second layer, and you see that they are more high level, more conceptual. And so after this layer, these pixels are flattened and passed to fully connected layers. Okay, so I send my code to the chat as this. And let's also briefly discuss the effects of learning rate and batch size. There is a task at the end of the notebook where you are suggested to change learning rate and batch size. Let's watch at the effects. So, for example, let's fix batch size and look at blue, green, and violet. Okay, как фиолетовый по-английски? Violet.
Purple.
Blue, purple. Thank you. Blue, green, and purple. So on training, we obtain that small learning rate blue is very slow. Then green is okay, and the purple is also okay. And in validation, we see that blue is okay, again, slow. So validation for blue is lower. So small learning rate is not good when training neural networks. Then purple is, green is the best one. And then purple is also lower than green. So small learning rate is bad because it will be too slow. Our neural network will stuck in some local optima. So the greater learning rate is better. And actually in SGD, bigger learning rate is usually, larger learning rate is usually assumed to be like a regularization. So a larger learning rate is better. But too big learning rate is also not so good. So green is actually in the middle. It's 0.01, and purple greater learning rate results in worse accuracy because it's too high. So you need to carefully choose learning rate for training your neural networks. And also, for example, let's look at green and red lines with different batch size. And what we see that with the smaller batch size, our train error is a bit larger, and validation too. So smaller batch size is also usually assumed to result in better quality. So if you use smaller batch size, you have more updates of your weights. But too small batch size, for example, batch size equal to 1 is also not okay because it will be very, very slow. So usually batch sizes of 32, 64, 128 may be used, but 64 is very popular one. So carefully choose learning rate and use batch sizes not so small but not so big. I think that's it. Now you have a break. So this was high-level interface of PyTorch. I think most of you have been already familiar with it, but usually there is often a scenario where students learn PyTorch like in Stack Overflow manner. So do not look inside code, only copy some code snippets and use them. And the goal of this seminar was that you understand what each line does and like organize some code file into logic parts so you understand what each part does. And in the next seminar, you will talk about low-level interface of PyTorch, how to compute gradients, some interesting tricks, and so on. So you will need it in a course too. Thank you all. Again, sorry for my bad English. Really, usually my English is better, but during lockdown, I do not have some abilities to practice, and it's not so good as it may be. Thank you. Have a nice day. And Oleg will begin, I think, at 12:15.
Thank you. Bye.
Thank you.
Bye.
Well.
Я думаю, что всем надо остаться в этом зуме. Сюда придет Олег, мне надо будет назначить его организатором. Сейчас пойду попингую Олега.
Hey.
Олег уже здесь, кажется.
Does anybody hear me?
Да. Сейчас я тебя сделаю организатором. Привет, Олег. Сейчас у нас перерыв пока. Я тебя сделаю организатором, и мы уйду. Окей?
Подождите, а пара в 15 минут или в 50? Я
15.
В 15.
Всё,
Да, в 15 же по расписанию. Давайте в 15. А то что вам тут сейчас сидеть полчаса ничего не делать?
Не, ну выбор между 15 и 20. Я бы в 20 сделал, на самом деле, даже.
Ну, давайте 20, окей. Ну, короче, я бы вам не предложила не сидеть тут без дела столько много времени.
Ну,
Все, короче, я тебя сделала хостом командой. Все, всем пока, всем хорошего дня.
окей, по времени пары, когда удобно? 15 или 20?
Да нам, в принципе, все равно, у нас потом еще пару, так что...
Ну, в принципе, можем в 15, да, начать. Ничего такого.
Хорошо, давайте. Всем добрый день. Соответственно, семинар у нас проходит на английском, но если у вас возникают вопросы, то вы можете спрашивать их на русском, ну или голосом, или в чате. Соответственно, что еще? Если будут проблемы со звуком, то тоже говорите. So today we consider PyTorch library. Well, a long time ago, when deep neural networks has just proved to be effective, there was no straightforward way to write your own neural network. I mean, to write neural network which is trained on GPU, you have to write C++ code with CUDA kernels and so on. But, well, because neural networks were necessary for the, for a lot of machine learning tasks, the machine learning libraries that helps to write neural networks appear. Such libraries are Caffe, Ciano, TensorFlow, PyTorch, Keras probably. The main common thing about these libraries is that they firstly allow you to do computations on GPU without writing a lot of low-level code. And second part, they have out of the box automatic back propagation. The thing you heard about in the previous lecture, I think. So I just pasted the link to our today's notebook in the chat. So you have to download it. Well, now the question: this size of notebook is okay, or you need a bigger font?
It's okay, yeah.
Oh, thank you. Okay, now another question. Did you use NumPy? Do you know NumPy?
Yes, of course.
Okay, perfect. So so it will be much easier to understand a torch. Well, actually, from one side, the first part, you can think of PyTorch as of NumPy with GPU support. So in NumPy, you can create tensor, reshape it, and do some basic mathematical operations with it, such as addition, multiplication, matrix multiplication, averaging, and so on. And actually, you can do the same things in PyTorch. Well, first of all, you can create torch tensor from NumPy tensor in a couple of different ways. You well, as in NumPy, you can change the type of your tensor, or you can create a torch tensor using just torch library. And with this tensor, you can do the same operations as in NumPy. But the naming on the of the functions and function arguments in PyTorch is slightly different from NumPy. So instead of dot, you have markmul. Instead of x along which you average your tensor, in PyTorch you have dim for dimension. But in general, the interface is almost the same. Okay, and you can not only import NumPy tensor into PyTorch, you can export PyTorch tensor back into NumPy. Right. Oh, well, actually, in PyTorch there are a lot of different functions, so naturally I will not cover all of them here. So if there is something implemented in NumPy, for example, you can try to find this the same thing for PyTorch in the docs or using Google Stack Overflow and so on. Okay, here we have a simple example how we perform mathematical operations over torch tensors. So here we make array with numbers from 0 to p, and then we just check that well, let's say Pythagore theorem in holds in PyTorch. But now we see it doesn't hold exactly because we have some floating point operations results. So one thing which is different in NumPy and PyTorch are so-called in-place operations. Well, in-place operations is operations which doesn't create a new object which contains the result of the operation, but modify the input object instead. So why do you need in-place operations? Usually the case is when you need to when you have a limited amount of memory and you need to well use it carefully. So the naming convention is that the mathematical operation with which ends with underscore in PyTorch is in-place operation, and the operation without underscore is not in-place operation. So the default, well, the default behavior for PyTorch is not in-place operation, which is more or less natural for neural network how to say, for neural network purposes. So in this example, we see that we have an array, and not in place operation doesn't change the original array, and in place operation returns changes the original array and returns its changed version. And here is the example where it might be useful. If you write, if we have, say, three matrices, and we do such, we want to calculate such an expression, we probably need three memory locations to get the intermediate tensor results. But we can do the same thing using just one tensor location and then applying in-place operations. So we first take y, then we multiply it by 2, then we in place add and subtract other two matrices, and this one is takes less memory and is probably faster because of that. But using this is not a common thing. Any questions so far? Okay. Now broadcasting. Do you know how broadcasting in NumPy works? Oh, great. Okay, so here we have the once again quite similar behavior. The point is that if we have say two two arrays with different shapes, for example, I don't know, let's make a different size of this arrays, and we want to obtain the matrix where the yj's element is the sum of of the first matrix i's element and the second matrix j's element. So if you want to get dyj equal to a0 plus b0j, we can use broadcasting. So if the if one dimensionality is the same dimensionality in one tensor is equals to 1 and in other not equals to 1, then the behavior of broadcasting is similar to that we expand the first tensor over this dimension to match the dimensionality of the second tensor, and then perform the operation. That's the thing. So that is how it works. We take 1 0 1 0 1 0 and add 1 1 1 2 in different rows to it, and we obtain such a matrix. And if you have any questions, you can read the docs once again. And here we have our first problem. The problem is follows. Oh, the question. Well, no, for well, okay, a lot of in-place operation that does not support backpropagation through them, so you just get some error if, when you call the backpropagation over the computation graph with in-place operation, but some operations which are invertible support in place backpropagation. So, for example, if you have leaky relay, you can do it in place. There is a flag to do it in place, and then you can backpropagate through such in-place operation. So there are some exceptions. Okay, the problem now is that we have a set of objects and a set of what we call them control points. All these points live in 10-dimensional space. So the objects are in matrix and the control points in the are in the matrix Y. The goal is to find for each object the index of the nearest control point and probably the distance to it. And naturally, well, just everybody can write a nested loop for this problem, but we want to vectorize it using torch operations in order to make it faster. So if the statement is clear, I just give you some time to make solution. Okay. Does somebody have a solution?
Yes. Should I say it or write in chat or
You
how
can
do you want?
write into the chat. The question was, does everybody have a solution?
Like, should I write it or not? I just don't understand.
Yes, yes. You can paste into the chat. Okay, and why is that?
Because matrix multiplication will do the how's it called? Will find yes, it's incorrect. Yes, that's absolutely bad idea because it's not. It's just scalar products, not the actual distance.
Okay, maybe other solutions. Okay, let's get to it. So the first solution is very straightforward. What do we need? We need to compute first of all, we need to compute the matrix of distances between each object and control point. So we can do it using broadcasting. We reshape the first matrix into this shape, and we subtract the reshaped matrix of points. So now is J's cos element of this tensor is the difference between the same dimension of one object and one control point. So we naturally compute the square it and sum over the last dimension and take square root. So now we have the matrix of Euclidean distance between each 2 points. And well, here it is. And to obtain the indices of minimal of the proposed point to each object, we would use argmin in NumPy, but in Torch we use just min. This function returns a tuple, the first element of which is the, well, okay, let us rewrite it to make it more clear. This is the distance matrix, and now we take minimum over the, which dimension? Over the last dimension. And the result, the tuple with the first element is minimum, and the second element is the argmin. So here is the vector of minimal distances, and here is the vector of IDs which we need. No, this tuple is not named. It will just oh, okay, yes, it's named, but I can see why it's important. Well, okay, this one would be more nice. I agree. Now, the drawback of this solution is that we have very large intermediate tensor of shape number of objects times number of points times the dimensionality. While actually we need only number of objects times number of points. Memory to store our distance matrix, and it is not clear why we have to use additional memory to compute it. And actually, the point is because we want the element of our distance matrix to be x y minus y j. Squared and the sum of this over k, we can use scalar product. We can say that distance between y and j's y's object and j's point equals to x squared minus well, surely we have some here, but we can just open well, the square, and we have x squared plus y g squared minus 2 times x and yj's. And now we see that this one is just matrix, well, just a scalar product between the object and the point. And actually, matrix multiplication just gives us this the matrix of such scalar products. But why the original solution was incorrect, we had not such additions to the scalar products matrix. So the final solution will look like minus 2 times x y plus x squared sum over to the last dimension reshaped to this shape. -1 means that the size of this dimension will be computed automatically based on the size of the original array. And the same thing for y. Well,
There is a type shape mismatch. You should have y transpose in matrix multiplication.
oh yeah, I see it. So now we have the matrix of distances, and we can check that we obtain the same answers. Okay, I believe that was more or less clear. So, interesting part now. How to do the GPU computations. Well, it is quite easy. We use actually three tensor methods for it. The first method is CUDA, which takes optional ID of the ID of the GPU you want to store your data on. CPU, which returns your tensor back to RAM, and the method 2, which can which returns the input tensor, which returns self if the specified device is the same as the tensor device, or it returns the copy of the tensor on the specified device if this device is different from the original tensor device. The main point is that you to make an operations, some mathematical operations over two tensors, they have to be on the same device, or both on the CPU, so in RAM, or both in the GPU memory of the same GPU, and you have to ensure that it happens. So if we, for example, I don't know, let's compute this one on the GPU. This one. If we have our tensor x on CUDA, and we try to multiply it by the tensor not on GPU, we will have error. But if we place both tensors on the GPU, we obtain some result. And well, here is the result. Just a tensor. And well, if you print this tensor without transferring it to CPU, well, you will see that the tensor is stored on CUDA, actually. It's stored on GPU. And well, I want to stress out again that these operations does not affect original tensor. So if we check what is white now, for example, it is stored on the CPU. Well, and one more point is the environment variable CUDA visible devices. So you just write something like equals to 1 or well, using this environment variable, you can remap the IDs of your system GPUs and the IDs of GPUs you use inside your program. So if you write well, something like that, then inside train PI, when you call CUDA without arguments or CUDA with zero ID, you will actually get into the first system GPU. Okay, that's all I have to say about it. Any questions? Okay. Now, the second interesting part about each dependent library is automatic differentiation. How it is implemented in PyTorch. The point is that in order to build a computation graph, we have to create a tensor before doing mathematical operations. We have to show that the tensor requires gradients, so we need to backpropagate to it. And when PyTorch sees that the tensor requires gradient, it begins to store the intermediate results, which we need to do backpropagation. So we create such a tensor. We then we apply some function to it, do some mathematical operations, and so on. Then we have a scalar. We take backward of it, and the gradient will be available in the grad field of the original tensor. And the same thing works for several tensors. So we can say A is a tensor which requires gradient, B is tensor which requires gradient, and so on. Then we have function of all these tensors, and we once again backpropagate through them. Well, yes, if we take a function, well, if we want to propagate from something and it have no computational graph, so to compute it, we didn't use any tensor which requires graph, you naturally get error. Once again, documentation official, you're welcome to use it. Well, actually, it seems more or less natural now, but the first dependent libraries used a different approach. That approach was called static computational graph, while PyTorch uses dynamic computational graph. So why dynamic? Because you build your computational graph through which you do backpropagation. When you, in the process of the computing the forward pass. For example, such libraries as Tianad or TensorFlow of the first version, or Cafe, they just first you define your neural network, which means that you define your computational graph. Then it, well, let's say compiles, actually turns into some executable code. For Siana, for example, you can see a lot of intermediate C files in the process of compilation of the model. In TensorFlow, it just well, turns into some inner representation. But the point is that once you define the computational graph, it is fixed. You just well, feed different input tensors to it. The pros of static computational graph is that once it is fixed, you can optimize it and compute everything more efficiently. But actually, in practice, we see that training in PyTorch and TensorFlow works in a similar time. So we have not big overhead for the computation graph. But now TensorFlow supports the dynamical computational graph as well in its second version, and PyTorch allows to export its models into static computational graphs, which are more suitable for production, for example, in Torch script. So once again, let's not dive deep into this topic, but you have documents once again. Okay, let's consider example. Here we have two different tensors which requires gradient. We compute the third vector, we turn it into some scalar, and we call the backpropagation from this computation graph. And naturally, we see that the gradient with respect to each component of the first tensor is just the value of the second of the same component of the second tensor, and vice versa, which is the correct answer. So this is how it works. Now detection variables. Actually, what does detach? It just interrupts or breaks your computational graph. So actually, it returns a copy of tensor, and the backpropagation doesn't go through this copy operation. Why do you need detection? Well, the most common error which I see in training loop in deep learning was not detaching loss variables. So imagine that you have your training loop and you want to compute some running average during your training loop to print on the screen, or to, well, I don't know. This is just nice. And you compute your loss function, and then you backpropagate through it, and then you add your loss function into well, to the to your average. If you do so, your average will be not just a number, it will be very large computational graph which includes all loss computation which you had in your training loop. So you will get out of memory error very soon, or not very soon if you're not so lucky, but you will get it anyway. So to avoid such an error, you can well, you have to detach your losses before average them. That's it. But actually, you can use it in your model as stop gradient. This is quite popular too. And there is in place version of detach, but I've not seen it used a lot. So here is the example. We have one tensor which requires that. We have another tensor which requires that, but we detach it and we once again compute the same expression over these two tensors. But now the first gradient is gradient, and the second gradient is known because we detached the original tensor from the computation graph. Now the important part, when you call backward 2 times, the gradient in the tensors are not overwritten, they just added to each other. So why do we need it? For example, you can artificially make a larger batches for your optimization. You can compute, well, if for example the maximum batch size you can store, you can compute on GPU is 16, and you want your batch size to be 256 due to optimization well, reasons of the problem. You can just take 16 batches, 16 objects each. Then 16 times you do compute loss and do backpropagation. And after that, the gradient variable will store the gradient for the tensor will be the gradient for the virtual batch of size 256, for example. And here we have the example of such behavior. We compute the gradient for x squared, where x is the tensor filled with ones. Actually, it is just 2. Well, the tensor filled with 2's. And the gradient for 1 over x is minus 1. But when we compute it and call backward, we get the grad equals to 1. So if you don't want such behavior, you have to manually fill with zeros your gradients between do backward passes. So here we do backpropagation and print gradient, then fill the gradient with zeros, And after that, you do backpropagation again and get the correct answer. Okay. This is it. Now, actually, the computational graph is a tree. So it have leaf. Well, okay. Maybe not exactly a tree, but anyway, there is so-called leaf variables. Well, actually, the leaf variables are just well, input tensors, the tensors which you are not well, the original tensors which requires graph, from which we start to build this computational graph. That's it. So when we call backward pass, the gradients are stored only in such leaf variables, leaf tensors. So x is a leaf tensor, y is not a leaf tensor because it is a result of mathematical operation, and p scalar is not a leaf once again. So that's what we see. Here is another example. We have two leaf variables. We have the two intermediate not leaf variables, and we see that not leaf variables have no gradients, and also each tensor have this leaf flag, which is true for leaves and false for not leaves. Okay. What if we need, for some reasons, to compute gradients for not leaf variables? For example, we need not only gradient with respect to x and y, but we need a gradient with respect to intermediate variable z as well. We can use the method retain grad for this intermediate result, but we need to call it before do backpropagation naturally, because otherwise, well, all intermediate results will be lost, and we will not be able to restore the actual value of the gradient. So here we have not leaf. We do some operations over it. We obtain our scalar, and then we call backward. Well, the point is that if you well, if you have no leaf variables, so actually all of your well, if all of your tensors doesn't require graph, and then you take some intermediate result and try to obtain graph from it, you will not be able to backpropagate to it because the computation graph was not built. So here we have the error. Okay. Well, but if we say that x requires grad is true here, it will work. Okay. Any questions so far? Okay, now we have the second problem. We want to do some optimization. The point is, well, the problem is follows. We have a set of points in 10-dimensional space. And we want to build a linear transformation of these points into two-dimensional space. So we just multiply them by some matrix and add bias. And we want that transformed points wise, we want them to lie around the circle with radius 1. So, well, we want to have a linear transformation which transforms points from 10-dimensional space into something like this figure. How do we do that? We just define a loss function which encourages our transform points to lie near this circle. And then we solve the optimization problem with respect to the parameters of linear transformation. So the point is that once we have automatic differentiation, we can how to say use something like declarative way to define the properties of our model. So we just construct a loss function which says which model is good and which is bad, and then everything such as optimization and so on will be done for us by the library. So which function you propose here is follows. First, we compute the norm of the transform point, which is Euclidean norm. Then we compute the distance of this norm to the one to the identity circle. We compute well L1 and L2 distances and take the weighted average. And this is the first part of the loss. Unfortunately, it is not enough because we can just map all the points into the same point, just to have zero matrix and identity bias. And therefore, all of the points will lie in the distance 1 from 0, but they will not be placed on the circle, and that is not a solution which we want. So we take the second part, which penalize the proximity of the mapping to the bias, well, to the central of this mapping. So first of all, we want this penalty to be 0 when the distance from the bias is larger than 1. And secondly, the closer the mapping to the bias, the larger is the penalty. So as we see, if this distance is 0, then this penalty is infinity, and if this distance is 1, then this penalty is comes to 0. So we have our loss function. We have to implement it, and this is how the original transformation works. Here it is. And after defining function, you have to write some optimization to obtain good linear transformation. Once again, you have your time. And if you have questions with respect to the statement or the solution, you are welcome. Any luck? Okay, let's get to it. So first of all, we compute our transform points. That's it. Now we compute their distance to 0. Well, quite simple as well. Also, we compute their distance to the bias. We will need to put into the second loss, so y minus now we have f0 as that's it, and f1 equals to 1 over yb minus 1, and well, clump for PyTorch is the same as clip for NumPy. So we just say that if something is lesser than 0, it will be 0. And then we return f0 plus 1 averaged. Okay, it works. Now, to the optimization part. What do we have? First of all, we need to say that our parameters require that. Second of all, train loop. Loss equals to f of wb. Well, one more check. Back forward. Here, well, it doesn't work because we have not enabled gradients, but now gradients are working. Why did I do that? Because originally gradients for W and B was none, and now it is some value, so I can write this thing. And now the problem is that if I write this code. For example, it contains an error. What is the error? Yeah, exactly. The problem is that since the W requires graph, we just continue to build our computation graph with this through this gradient step. So how can we handle it? The first way is to use this data field, which just well shows stores what's inside this tensor, and well, if you write such code, we will not build further computation graph. So let's check it out. Okay, once again, here we need detach. Well, not so good, but we have not so many iterations now. More well, elegant way to solve the problem is using no grad context. What is that? It is just well, probably you know what is context in Python. Well, even if you don't know, the point is that inside such construction, no computational graph is built. So you say to PyTorch that we don't need gradients inside this. So once again, we can and where is the gradient? Okay. That's right. What happened? Oh, I see. So, well, if we run it for a long time, you will get something like this. So, well, for me, it is interesting that we have such a linear transformation which maps normally distributed points in 10-dimensional space to 2-dimensional circle. But the point is that this is well, is how can we implement optimization in PyTorch? Well, naturally, nobody does that because we have optimizers in torch.optim module, and we used them in the previous seminar, and that's how we need to do it. So now I think we have no time to do the rest of the notebook, so I'll just give you a brief about what happens there, and you can do it in your free time if you want to. So what do you have here? Well, we want to write our own neural network, and to solve some classification problem. It is digits classification problem here. We do well. We turn that numpy arrays into torch tensors. We do some normalization over them. The point is that to understand the PyTorch model structure, you can implement the similar structure by yourself. So what methods are necessary in such structure? Firstly, it has to maintain the list of its children. So each neural network must maintain the list of its layers. Secondly, there must be a recursive function which returns the list of parameters of the neural network. And there are some functions which turn the neural network from train to test evaluation mode. Well, what does it mean? It means multiplication by the constant instead of sampling for dropout, as you were told on the lecture, or it means using running averages instead of actual mean and average in batch norm, and so on. So now, once we have this original model class, you can inherit different layers from this model, and here we just re-implement parameters function. But in PyTorch, we define our parameters with neural network parameter wrapper. So, well, if you have some weight W inside your PyTorch neural network, which requires graph, you have to wrap it into such wrapper, which tells PyTorch that this tensor is a parameter and nothing else. So, and each layer have it forward function, actually, which is called when you just call your model. Here is different layers, and here is the layer which defines network, which contains a sequence of different layers. And here is a loss function, and here you can implement different optimizers. So just stochastic gradient descent, and well, after that, stochastic gradient descent with momentum, and MSProp and ADAM, not so hard actually. And here is example of train loop with Ryan average, for example. And for those who, well, mm, mm, more interesting, we have dense layer with dropout. So here we can use the benefits from the dynamical computational graphs, which so the point is that if we have dropout, we zero some activations, and actually we have no point in multiply them by the next linear layer, because we just multiply zeros. So we can avoid such computations and probably speed up our program. So here you can implement dense layer with dropout, which well sees which columns of the input data are zeros, and then select only non-zero columns from the input activations, and then do reduced well, the matrix multiplication with the reduced input size. And actually, when you done it, you will find that you can observe some speed up only for very wide layers and for very high dropout rates. So it is not practical at all. But probably it is interesting as well. So probably we are out of time. Do you have any questions regarding the seminar? Okay, so thank you for your attention and have a nice day.